So today we'll talk about simple harmonic motion in a car. This is related to Module 3 of simple harmonic motion, specifically on Hooke's law and damping. So we'll talk about the car suspension system and how that is related to simple harmonic motion. We'll also talk about the compression and the expansion of spring, which will reduce the shock to passengers. So how the suspension works is the suspension of a car is a damped spring that produces an opposing force when it is compressed. The springs sustain the weight of the vehicle, and the dampers oppose the spring movement by dissipating their energy, which prevents them from bouncing without control. To briefly talk about Hooke's law, basically the force that is produced by the springs depend on the distance they are being compressed. And this force is given by Hooke's law, where force equals negative k times x, where k represents the stiffness of the spring, which is measured in newtons per meter, and x represents the contact depth in meters. And the force that is produced by the dampers depends on how fast the suspension is being compressed or elongated. And this is also known as contact speed, as it will oppose this movement. Thus, the force produced is proportional to the contact depth. The suspension distance is the compression limit of a spring. This means that beyond this point, the spring has reached its maximum force and cannot compress any further. The suspension position is also known as the contact depth, where the spring force matches exactly to the force applied on the spring. Therefore, the more weight that is loaded on a wheel, the more compressed the spring will be, and the suspension position will be lower. The overall suspension force is calculated from the formula suspension force equals k times x plus damper times contact speed. If the force produced by the suspension is at a specific steady state where contact speed is 0, the equivalent sprung mass can be calculated with the formula sprung mass equals suspension force over gravity. Using the sprung mass, you can calculate the natural frequency for that spring under that particular load. This can be calculated using the formula natural frequency equals square root of stiffness over sprung mass. And the concept of sprung mass can also be used for studying the damping behavior of the car, which will be explained in the next slide.
In a harmonic oscillator, damping is known as the frictional force that dampens the motion and causes the system to lose energy over time. The damping force is proportional to the object's velocity, calculated with the formula force of damping equals negative b times v, where b is the damping constant in kilograms per second and v is the velocity of the vehicle in meters per second. For a car traveling at high speeds, damping comes from the hydraulic dampers present in the suspension system. They are composed of a piston inside of an oil-filled cylinder. They work to dissipate the high amounts of energy in the springs. When there is no change in energy in the springs, like when the car is at rest or at constant acceleration, the dampers have no effect. The damping rate can be calculated using the sprung mass and the damping ratio. The formula for deriving the damping ratio is the damping rate divided by 2 times the square root of stiffness times sprung mass. If the damping ratio is greater than 1, the system is overdamped. If it is exactly 1, the system is critically damped. And if it is less than 1, it is underdamped. For most vehicles, the damping ratio is around 0.2 to 0.4, meaning it is an underdamped system. In a real vehicle on the road, the frequency and damping ratio are not constant. They would be changing all the time depending on whether a car hit a bump, is accelerating, or turning. However, we can still study the oscillating behavior by isolating each individual situation. This concludes our presentation.